Hello, and in this video we're going to talk about rational functions. We're going to split this up into two videos. The first part we're going to just talk about the toolbox functions. That's the inverse proportional and the inverse proportional to the square. We're going to look at the asymptotes for both of those, horizontal and vertical. So in this section we're going to look specifically at those two functions. So the inverse proportional function is the function f of x equals 1 over x. So it looks like specifically it has certain points that it goes through. It goes through 1, 1. It goes through 1/2, 2. And it goes through 2, 1/2. So it goes through those points specifically, and it curves this way in the positive region. It also has the points on the negative region, which are the exact opposite. It's going to have negative 1/2, negative 2, negative 1, negative 1, and negative 2, negative 1/2. Those are going to be the points down here. It's going to look like this down here as well. Okay, it has one horizontal asymptote. Now an asymptote, horizontal asymptote, is where it approaches as it moves to the right or moves to the left. So the horizontal asymptote here is y equals 0, or the x-axis. The vertical asymptote is the line that it doesn't cross vertically. Now, it can cross the horizontal asymptote. It just approaches this value. So this is the value it approaches as it goes to infinity and negative infinity. So on horizontal asymptote, it can actually cross the asymptote, but it's got to get close to that value. So it's getting close to this value as we get big or small. So it approaches, so we can say over here that approaches y equals 0 as x goes to infinity or x goes to negative infinity. So it approaches that value of 0. Now the vertical asymptote is different. It's going to be, in this case, it's going to be x equals 0 because it's the y-axis. And we can't, it doesn't cross that point. It can't go across the axis and come back around on the other side. It has to approach the axis, but it won't cross. So this one, in this case, neither one of them cross, but in the future this can actually happen. A horizontal asymptote can actually cross and then approach the value. We'll see that later on in a couple examples. Okay, now you need to know that we will want to be able to translate these in our transformations. We'll want to be able to take this function and transform it by moving it right, left, up, or down, and stretching or shrinking it. So that we can write those functions, those transformations, as we can actually write them in there. We can write them like this: f of x equals a over x plus a number b plus a c value. Actually, this is going to be a minus down here. minus b over c. So if we write it like this, then we have some transformations. We have a stretch or shrink because of this value here. We have a horizontal conversion for this, and we also have a vertical up and down by this function. And if this is negative, we have a reflection. Okay, so there could be 4 transformations there. So if the 4 transformations are A gives you a vertical stretch or compression, and it also will reflect if negative. Now it's stretching if we have A is going to be greater, the absolute value of A is greater than 0. Or greater than 1, sorry. If it's greater than 1, that means it's bigger than 1. Then it's going to be a stretch. If it's between, if the absolute value of A, because we want to make sure that if it's negative, we just reflect it. If it's between 0 and 1, then it's going to be a compression. Okay, and then B shifts horizontally, and C shifts vertically. Okay, so this is our transformation of what we would see in this kind of function. We would take this function and we'd move it, we could stretch it up and down, or we'd move these points by a factor, the y values by a certain factor, and then we would do that. Now let's look at an example. Now these transformations can be hidden in another function. So what we have to do is, if we see a function that looks like this, ax plus b over cx plus d, if we see a function like this, this is the same thing, but it's just, what we have to do is we have to apply long division to convert to the transformation form. Okay, so if we see a problem that's like this, where we have a linear function over a linear function, then that's going to be the same thing as a transformation of this graph. Okay, so let's look at an example of this type. F of x equals 3x plus 2 over x minus 5. Okay, so this is, we're going to transform this into that graph and then look at it specifically as a transformation of the other graph. So what we would do here was we would take the x minus 5 and we would divide it into the 3x plus 2. So that would go in 3 times, so we'd have 3x minus 15. Okay, and then we'd subtract, so that'd be 17 here. So that means that this is the whole number, this is the remainder. So this function can be written as 3 plus 17 over x minus 5. Therefore, now we have it in the right form. So this is a stretch by factor 17. We have it moves right 5, and then up 3. So that's that transformation. That's what would occur in this thing right here. We would transform that graph, this basic graph right here, by these transformations in order to get it to look like that. So it doesn't. So basically, on this one, my horizontal asymptote would equal to y equals, since we shifted it up 3, so it would be y equals 3 because we shifted it up 3. It was at 0. And my vertical asymptote would shift from 0 vertically to right 5. So that would be x equals 5 would be my vertical asymptote on that one. Okay, so that is the basic inverse proportional with its asymptotes and transformations. Okay, now inverse square function is 1 over x squared. Its basic graph looks like this. It goes through 1/2, 4, 1, 1, and 2, 1/4. So it's squished a little bit closer to the axis than the other one. And it does the same thing but mirrors over the y-axis on this side. So it's a mirror over on this side for this. So it's going to be negative 1/2, 4. The y values stay the same. Negative 1, 1, and negative 2, 1/4. So those are the values that are on the graph. It looks like this in general. It has a horizontal asymptote at y equals 0 and a vertical at x equals 0. So the only difference between this and the other one is that the second part of the graph is not down here, it's going to be up above because we're squaring it. And it's a little closer to the axis. After it hits 1, 1 and negative 1, 1, it squishes a little closer to the axis faster because of the square. So this one doesn't have a nice transformation, or it has the same transformation as the other one, but it doesn't, we can't just divide. Not all of the ones that divide will come into this function because we have to be able to factor it into this thing here. So we have the same type of thing here, so it's the same form. This is the form you'd see. This would be the stretching or shrinking, and could be reflection. This would be the transformation right or left. If this was positive, then it's going to go left. And this is the transformation up or down. So it's the same as the other one here, but it's going to be a graph. This graph's going to be up here instead, or it's going to be branched in the lower quadrants if it's negative. We don't have something like this specifically for this second function because we have to have a perfect square down here, and not always that factors into that way when we have a function that has x squared on the top and x squared on the bottom. We can't always factor the bottom into this, therefore they don't always fall into that category. So in this section, if you're going to be dealing with this, then it's going to be written in this form for you. If you can factor it this way, then it is a transformation of that type of function. But we're going to look at specifically in the next video just general rational functions. So we're going to move on to that next.